we've seen this slide a zillion times before. Projectile motion, key ideas are that the velocity in the x direction is a constant. It doesn't change. The velocity in the y direction does change. So the first step to doing any problem is going to be to come and calculate the velocity in the x direction and then the velocity in the y direction. But remember, that's the initial velocity in the y direction because the velocity in the y direction changes. The velocity in the y direction is going to be affected by gravity. So classically, one of the first questions that comes in is how high is, what's the maximum height? So to get the maximum height, what we'll probably do is use the fact that the velocity in the y direction at the top is 0. So the key part being that the velocity at the top in the y direction is 0. So I'm free to use my v squared equation. The velocity in the y direction squared is velocity initial in the y direction squared 2a delta y. And since this term here goes to 0, it's pretty straightforward to get the height. And remember, for this equation, all of the velocities, accelerations, displacements have to be in the same direction. So the next step is to ask the question, are we trying to figure out how far the thing goes? So if I'm trying to calculate a distance in the x direction, question mark, what I'll use is that the time to go to y equals y final. So for example, if I've got a ball that's tossed starting here, comes back to Earth again, then maybe I could use this equation right here and substitute in this height of 0 and that height of 0. And then I can solve for time. That's probably in some ways the most simple case. If I were trying to figure out, let's just quickly, if I have a ball going up and hitting a wall, I know the distance in the x direction, I know the velocity in the x direction is v0 cosine theta, so I can get distance in the x, velocity in the x times t. I can solve for time, and then if I know time, I can go the height in the y direction is the initial height v0y t 1/2 minus 10 t squared. I could also calculate the velocity at that point. V sub y is v0y plus at. Again, that's minus 10. If vy is a positive number, it's still going up. If vy is a negative number, it's going up. It's coming down. This is the range equation. The range equation is useful provided y final equals y0, and it tells us how far the thing, what the distance in the x direction that the object will go. The maximum range is at theta equals 45 degrees, obviously because sine of 2 theta would be sine of 90. Sine of 90 is 1, and therefore that tells us how far, that tells us the maximum range. So let me move quickly. One of the interesting things that happens is, again, we've said that at 45 degrees, we get the maximum range. And what happens is that if I have a shallower angle, it goes like that. Because basically I don't have enough y velocity to keep it up in the air longer to get any distance. And if I have a steep angle, it's still not going to go far enough, because in reality, although I have lots of time, I don't have a very big velocity in the x direction. So all that time up in the air is, so to speak, wasted, depending on what you want to do, right? And if you're a football player and you punt the ball, you want to punch it high enough that you can get all of your defenders right down and to tackle the guy, to smuckle the guy who gets the ball. On the other hand, maybe there's might be motivations to make the thing be very shallow, so it happens very quickly. I don't know. You had a question? Yeah, Sam?
Yeah, so it's just kind of like an optimization problem, right?
Yeah. But there is, we know the optimization is that range equation. Okay. What else can I tell you? Let's go back to the first slide. Imagine I have the ball off a cliff. Imagine that I launch a ball, velocity 20 meters per second, angle 37 degrees. What's the first step to solving any one of these projectile problems, Carson?
Figure out the
Right, perfect. So almost no matter what I do, V0 in the x direction, 20 cosine 37 degrees, 16 meters per second. V0 in the y direction, 20 sine theta, or 20 sine 37, sine 37, 12 meters per second. Let's assume this has a height of 15 meters. So I want to know when the ball is going to hit the ground. So in the previous problem, we knew a distance to the right, a distance in the x direction. In this problem, we know a distance in the y direction. So I'll use y is equal to y0 v0 yt 1/2 a t squared. And I'll plug in the numbers that I know. Now the question becomes, am I going to call this height y equals 0, or am I going to call this height y equals 0? And I can do either. I'm going to, just for sport, I'm going to start by saying that y0 is equal to 15 meters. So I start at 15 meters, and I want to end up at 0 meters. So 0 is 15 plus velocity in the y direction, 12 meters per second, times t minus 5 t squared. I can solve that for t, and I'll actually get two numbers. One's going to be a negative, one's going to be a positive. I can take those numbers and plug that in. The distance in the x direction is velocity in the x direction times t. Is anybody really good with their calculator and plug that into have the quadratic formula? What's the two numbers? Oh, the positive one.
I think it's the wrong note.
I don't know why I'm asking you to do it. I got a calculator too. Program. Execute. Program.
I got 3.3.
3.3?
Time.
Yeah.
3.3. And so, we can just say 16 meters per second, 3.3 is the final distance. We could talk about a final velocity magnitude is going to be the square root of Vx squared, Vy squared. And we know Vx to be 12 squared, and Vy is going to be, Vx is 16. Vx is 16, quantity squared, and then Vy is going to be 12 plus minus 10, 3.3. So that gets me 21 meters per second, 21 meters per second squared, and that will get me the velocity. And then if I'm going at 16 meters per second in the x direction, and I'm doing 21 meters per second in the y direction, I can define my angle by saying the angle is equal to the arc tangent of opposite 21 over 16. Just repeat the question one more time.
Should we use negative 21 meters per second for the y velocity or positive?
So I drew that angle. So I would probably stick with positive 21, but know that I was below the x-axis. If you plugged in, if you said, you know, the arc tangent of minus 21 over 16 is equal to theta, then you'd have to be smart about, you know, kind of, it's going to give you either this angle right here or this angle right here. So you have to just make sure you were smart about it. Follow what I'm saying?
Yeah. Also, which angle is theta defining? Is that the ending angle?
That's the ending angle. That's the velocity with respect to the ground. So it would come in, it comes in like this, right? So you'd have to be smart. That's why I say always draw a good picture. Okay. On the table is angular velocity / acceleration. And we're going to come back to this in a couple of chapters. But since we mentioned it once, we're just going to kind of deal with it. So suppose I have an object that's going around in a circle, maybe a record player, and I want to describe the motion of the record player itself. One thing I can talk about is the fact that a typical record player is 33 1/3 RPM, 33 1/3 revolutions per minute. So I can define a velocity based on that by saying that velocity is equal to 2 pi r over t, the time it takes for one cycle. So t is equal to the period or the time for one cycle, or time for a revolution. And one of the interesting things is that no matter where I am on the circle, I still have the same, I still make the same number of revolutions per minute. So if I want to figure out how fast I'm going, though, it's going to depend upon how far out on the circle I am. Right? Does that make sense? And so you can do conversions. You can talk about, you have a breadcrumb on the edge of a record player, that's spinning at 33 RPMs, what is the velocity of a point at the end? What is the velocity of that point? The other thing that's interesting, what the angular stuff comes into play is I can any radians I go through in a second, right? What angle, at what rate does the angle change? So we'll start by reminding ourselves that the distance I travel d, the distance is equal to the radius times the angle. So that angle would be theta, and that's the radius. And so that if I want to know how fast a point is going at the edge of the wheel, I would say that the derivative with respect to time of that displacement is equal to the radius, which is not changing, times the rate at which the angle is changing. We know that this here is just the tangential velocity, the instantaneous velocity of a point. And that's equal to the radius, and then we call this omega. It's a Greek letter omega. Okay? So if I ask you for angular velocity, that's omega, and that just equals the velocity divided by the radius. So kind of like it's a normalized velocity, because the beauty of this is that every point on this record has the same angular velocity, but its linear velocity depends upon how far out from the edge it is. Yep.
So is that in radians per second?
That's in radians per second. Great question. And then we can play the same game and say that the derivative of v sub t with respect to time is r times the derivative of omega with respect to time. And this is tangential acceleration is the radius times the angular acceleration. Guys, and just as a reminder, in case it's not obvious, that alpha, just as a reminder, in case it's not obvious, alpha is equal to the angular acceleration and that has units of radians per second squared.